Well, hello everybody. Good afternoon. I'm Chris von Willer, Chair of the Warren Centre, and it's my pleasure to welcome everyone today to this magnificent auditorium, the Chow Chak Wing Auditorium, for the Warren Centre Innovation Lecture. Warm welcome also to those joining us via live stream online. Before we begin the proceedings in the usual way, we'd like to acknowledge, pay respect to the traditional owners of the land on which we meet today, the Gadigal people of the Eora Nation. It's upon their ancestral lands that the University of Sydney is built. So the Warren Centre Innovation Lecture now is 25 or 30 years old. It's an institutional lecture. The focus is innovation, which back in the 80s was a fairly esoteric concept, but today it's absolutely mainstream, central to productivity, to wealth creation, and to the prosperity of the nation. And so much of important innovation comes from public places such as the University of Sydney. So last year's theme, you might remember, was on space, and you may be aware that our innovation lecturer on that occasion, Catherine Bennell-Pegg, after the lecture was selected to train as an astronaut. So Branka, big things in store for you today. This year we're diving into the rapidly evolving domain of wireless communications. This field has had a rich history of innovation, with Australia, as I'm sure you know, a leading world contributor. So one of the most important of those contributors is this year's Warren Centre Innovation Lecturer, Professor Branka Vucetic. And I'd now like to pass over to the MC today, Jeff Lee, who will outline the proceedings and introduce Branka. Jeff.
Thank you, Chris, and welcome to the Warren Centre Annual Innovation Lecture. We have an in-house audience, and as Chris said, we have several hundred people also online. For those of you here in the museum, a couple of housekeeping items. In case we have to evacuate, please exit the room as you came in, and the nearest fire exit is out the main door, located straight ahead on the left. Follow any instructions from fire wardens, etc., and the evacuation point is in front of the Great Hall across the quadrangle. The nearest bathrooms are down here, just outside and on the left. There will be a Q&A session at the end of Branka's presentation, and if you're online, you can send your questions via the Slido function at the bottom of your screen. Professor Branka Vucetic is an internationally recognised expert in coding theory and its application in wireless engineering. Professor Vucetic has had various research and academic positions globally and here in Australia. Since 1986, she has been with the School of Electrical and Information Engineering here in Sydney University, where she is currently the Laureate Professor and Director of the Centre of IoT and Communications. Her research includes wireless communications, digital communications theory, error control coding, and multi-user detection. Branka, can I call you Branka? Branka has published 4 books and more than 300 papers in telecommunications and conference proceedings. She is a Fellow of the Australian Academy of Science, a Fellow of ASCI, a Chinese Government Friendship Award recipient, an IEEE Fellow, and a former editor of the IEEE Transactions on Communications. Her current research activities are focused on advances in wireless networks and the Internet of Things. She is working with her team on developing a fundamental theoretical framework and advanced signal processing and network protocols for millimetre wave systems. That's below the gigahertz communications. In the area of Internet of Things, her focus has been on providing wireless connectivity for mission-critical applications where ultra-low latency and ultra-high reliability are essential. Examples of this are automated power grids, information exchange between vehicles for detecting safety critical situations, and remote robot-assisted medical surgeries. A further issue that she's addressing is developing wireless power transfer systems for delivering energy to communication devices via microwave and millimetre wave radiation. The opportunity for large-scale deployment in wireless sensing networks and IoT is endless, as many of you know. Now, outside all that activity, academic activity, Branka is also, I found out, a very passionate line dancer. And she's participated in many countries in this region and across the world. So, ladies and gentlemen, Professor Branka Vucetic.
Hello, everyone. Thank you, Chris and Jeff, for the kind introduction. And thank you to the Warren Center team for inviting me to present the innovation lecture. I'm truly honored to be here today. So the title of my talk is Wireless Networks for the Digital Age. And I will talk about wireless cellular networks, which revolutionize the way that we live, learn, communicate, and do business. In particular, I will present the vision, technologies, and applications for 6G and examples of my team's contribution to the 6G development. My research was inspired by two extraordinary visions. The first one is from Nikola Tesla, almost 100 years ago, who stated that wireless can be used to convert the whole Earth into a huge brain to be accessed with small devices that could fit into our pockets. So this is quite a precise prediction of the mobile internet. Wireless is an extremely hostile medium with noise, interference, and fading affecting digital signal transmission, in general signal transmission. And this is why it took several decades from fundamental concept to the commercial deployment of analog wireless broadcasting of TV and radio. The next real breakthrough came with the digital vision from Claude Shannon from 1948. He stated that if we transmit information in digital form at a rate below the channel capacity, it would be possible to have an arbitrarily low probability of error if we use error control codes. He didn't say how to design these codes, just that they existed. My research was aimed at designing error control codes in order to achieve the first vision of reliable and efficient wireless communications. And it took 50 years to the research community to design error control codes that reach the Shannon capacity limit. And Shannon actually defined this limit as a function of the signal-to-noise power ratio and the bandwidth. The advancement in error control codes parallel the evolution of wireless cellular networks from 1G to 6G, and error control codes contributed to the exponential increase of data rates from 2.4 kilobits per second in 1G to 10 gigabits per second in the current operational wireless cellular network, 5G. One of my research highlights was adaptive error control codes. So error control codes introduce structured redundancy at the channel encoder here at the transmitter. And that structured redundancy is used here at the channel decoder to correct errors that occur in the channel due to noise, interference, and fading. Prior to this invention, the amount of redundancy was fixed and selected according to the worst channel condition. That was an overkill, and selecting the amount of redundancy for the worst channel condition reduced the possible channel data rates. So my idea was to actually measure the real channel state condition by measuring the signal to noise power ratio, sending that information back to the encoder, and selecting the amount of redundancy for the actual channel state. This resulted in a 50% increase in the average data rate, and the method was accepted as a standard in all wireless communication systems. And this is the publication which reported this invention. So the method was first used in satellite communications to combat rain fading, which prior to this was managed by increasing the signal power, which was very expensive because of long distances, and later was also used in Wi-Fi and cellular networks to adjust data rates to the distance of devices from the base stations. So having high data rates if they are closer to the base station and lower if they are further. Apart from design of error control codes, my team and I worked on the design of wireless network receivers in mobile phones and base stations. As opposed to error control codes, which are standardized and fixed for the duration of a wireless standards, and wireless receivers are not. So manufacturers distinguish their products by developing proprietary technologies for receiver design. We worked with a number of international companies in developing wireless receivers, which means detectors and decoders for them, and across the several generations of wireless cellular networks. For example, soft output detectors and decoders for 2 and 3G for Nokia and Ericsson, adaptive minimum mean squared receivers, digital filter-based receivers for 3G for NEC, power interference cancellers with decision statistic combining for 4G for NEC, and Bayesian and AI receivers for 5G. This has been patented by the University of Sydney, and there is interest from a Wi-Fi company in taking a license. And these are the publications which reported these inventions. The current wireless cellular network is 5G. Prior to 5G, cellular networks served only an information channels, supporting communications between humans and the internet. 5G aim was to expand the range of applications. And for that, it introduced 3 different types of services. The first one, called enhanced mobile broadband, is in fact an improved 4G with increased data rate from 100 megabits per second to the maximum 20 gigabits per second. And it is used for streaming of high-definition videos and movies for smart offices and mobile cloud computing. Apart from this service, 5G introduced 2 machine-to-machine type communication services. So the first one, called massive machine type communication, MTC, provides dense connectivity for IoT sensors that could be used for connected homes, for wearable devices, environment, and traffic monitoring. They're usually low data rate, low power devices with high density connections. And the KPIs for this service were 1 million devices per square kilometer and 10 years of battery life. The second machine-to-machine communication service for IoT is URLLC, ultra-reliable low-latency communication. And that is aimed to provide communications for mission-critical services in autonomous driving, industry automation, energy grids, and healthcare for remote surgeries. And for this application, there are two critical things. First, that latency has to be very low in order to provide stable control, and reliability very high because these mission-critical applications are not allowed to fail. So the reliability has to be 4 nines, which means that for 99.49% of time, the network has to be fully functional. However, in real networks, which have been deployed in most countries worldwide, the KPIs are lagging behind the projecting ones. So for example, the data rate, maximum data rate is 10 gigabits per second, not 20. Then the latency is several milliseconds, up to tens of milliseconds. And the density connection is maximum 50,000 rather than 1 million. Which means that we need to continue working on developing wireless technologies, and the research community in wireless communication is now engaged in developing 6G. So 6G will bridge the gap between what the current and emerging applications will demand and what 5G can offer. And it will evolve from 5G, as 5G evolved from 4G. So the main current 5G application, EMBB, Enhanced Mobile Broadband, will evolve into holographic connectivity to support 3D holographic transmission for ultra-high fidelity virtual and augmented reality, for telepresence with high fidelity and multi-sense experience. And the KPI for this application will be high data rates and low latencies, because for VR, AR, if latency is high, then the users will experience motion sickness. In some applications, like industrial automation, autonomous driving, and healthcare, there will be a need for simultaneously meeting both URLLC and MTC machine-to-machine performance criteria. So these two services from 5G will be integrated into one called deep connectivity, and they will be used in these mission-critical applications. With the KPIs being high reliability, ultra-low latency, the high connection density, and high battery life. 6G will introduce two new services, ubiquitous connectivity and bioconnectivity. 5G has a limited range and limited coverage, focused mainly on urban areas, while 6G aims to provide all coverage across space, air, and ground and water, with services providing space communications, possibly communications with lunar and Martian colonies, underground, the underwater exploration and research, and underwater robotics. Another new application is bioconnectivity to provide communication between wearable and implantable biosensors with external devices for health monitoring and diagnostics. And there might be possible brain-machine communications by developing new neurotechnology devices and brain-to-brain communications. Each generation of wireless cellular networks has its killer application. Though we thought that IoT would be a killer application for 5G, it is still not there yet. So we can say that for 5G, the killer application is streaming of high-definition videos. Well, for 5G, we can only speculate. So I predict that it could be telepresence, where the users will experience the remote physical environment with lifelike fidelity. And they will communicate with digital twins of other humans and physical objects using multisensory interactions. So that means including touch and smell. "6G most likely will have different devices than 5G, and we have already entered post-smartphone era. So with smart watches, smart bracelets, and in the future we might have direct brain-to-brain interfaces, which is still in the domain of science fiction. But you know, if we go back to these visions of Tesla and Shannon, they happened. It took a long time, but now this gap of going from a vision to the actual implementation with the increased speed of the development of technology might be shorter. The applications that we listed will mandate the 6G KPIs. So for AR and VR, augmented and virtual reality, we will need much higher data rates than we have today and much higher network capacities. So the KPI for data rates in 6G will be at least 10 terabits per second, and the network capacity should be increased 10,000 times in order to support these services. For mission-critical applications where we have control, the latency should be below 1 millisecond, of the order of 10 microseconds, and with high reliability with 7 nines. And for mission-critical applications and deep connectivity, we will need increased battery life and high density of devices of 100 devices per cubic meter. 6G will have 2 new KPIs of energy efficiency in order to reduce the effect of many digital devices on the climate change. So it needs to be increased 10 times from 5G. And another one is centimeter level positioning. So 6G will have not only communication functionality, so it will provide control and positioning. And so it is required for in indoor applications in construction, in manufacturing and healthcare, that the accuracy of indoor positioning is of the order of 1 centimeter. To get these ambitious KPIs, we need to have new technologies. And so the increase in data rates will come from increased spectral efficiency, which we can achieve by design of new error control codes, by design of new non-orthogonal multiple access schemes, 3D networks, large intelligent reflective surfaces that serve as roads, walls, and entire buildings. They will provide line of sight communications and reduce the effect of interference. 6G will be implemented as an intelligent platform with integrated communications, computing, sensing, and localization, and will serve as a plug-and-play platform for new IoT services, so that those who develop these services don't need to worry about communications control, sensing. They will just need to develop their own applications. And each wireless generation has its own key technology. So it is predicted that for 6G, it will be AI. So this will bring us to the question why we are going to use AI in wireless when we have a long history of developing many theories in wireless communication, starting from analog and digital communications, information theory, signal processing, statistical theory of communications, error control coding, and digital filters, for example. So why we need AI now? And so there are two reasons where we can use AI to outperform analytical methods. So if we don't have mathematically tractable models of channels and propagation in wireless, or if they are not accurate enough, then AI gives better results. Also, in complex optimization problems that we use for resource allocation, for base station positioning and routing, AI can give us methods that operate in real time, while these analytical methods, which are very complex, with the complexity increasing exponentially with the number of users, cannot do it in real time, cannot be deployed in real time. And we will show actually that AI is not enough, that we still have to combine AI with analytical methods in order to get the best results. And there is another connection of 6G with AI. It is through this platform that I mentioned, that 6G will provide combined communications with computing by bringing AI capabilities from the cloud to devices and the sources of data for many reasons, to protect privacy and security, for reducing latency, and for reducing the cost of transmission and congestion of wireless networks. So here I show some use cases where we used AI in our Center for Design of Wireless Networks. And the first one there on the left is the AI for physical layer design. The physical layer is the lowest fundamental layer in the network system model, which deals with data transmission, electrical signals, and radio waves. And we used AI there to design error control codes and receivers, mainly because we don't have accurate channel descriptions, in particular in case of interference. Then we use it for propagation modeling. Propagation modeling is essential for base station positioning. And right now, we don't have good analytical models. In fact, we don't have analytical models. We use empirical models for propagation modeling in wireless. And so by using AI combined with analytical methods, we achieve much better results there. Then in network resource allocation, in networks, we use optimization problems to allocate network resources such as power and bandwidth to multiple users. And the complexity of these optimization methods increases exponentially with the number of users. So in order to implement them in real time, we combine analytical methods with AI to deploy them in real time. And this is communication in control co-design. As I said, we have to provide control functions together with communications in 6G. Not only control, we need to provide sensing and localization. And so there is an emerging area of wireless network control. We use wireless communications to control various physical processes and objects, in particular in industrial automation. Right now, we cannot design jointly communications in control, though it would be beneficial to do it because there is correlation between these two processes. So we design them separately because it's too complex by using the current analytical models to do it jointly. However, if we use AI together with analytical models, we can get much better results for both communications and control. So we have done that as well. And similarly, we did that, used AI with analytical methods for joint communications and localization, which is not shown here. So now I will show some of the results that we have achieved in our center, and I will focus only on the physical layer design for coherence and connection with our previous work in this area. So I'll start with error control code design for 6G. In 5G, we have two types of codes that are used, one for the data channel, which transmits information, and for the data channel, we use low-density parity check codes, LDPC code. And for the control channel, which transmits control commands between devices and the network, we use polar codes with cyclic redundancy check CRC. Both of these two codes, LDPC and polar codes, are very good codes which approach the Shannon capacity limit if they are very long. So that means tens of thousands bits long. And so the choice of LDPC codes for the data channel is good here for EMBB, where we have very long packets. So this is the service enhanced mobile broadband, where we have very long packets of tens of thousands of bits, and LDPC codes approach the Shannon capacity limit. However, LDPC codes are very bad for short lengths. And we have to have short lengths for URLLC in order to achieve low delay, because the delay depends on the length of the packet. And so that means that these codes that are selected now for URLLC have very poor performance, where they really should have much better performance because we have to achieve ultra reliability for URLLC. So that means that for 6G, that needs to be changed. Then for the control channel, we have polar codes. These codes are also very good for long packet lengths. They're better than LDPC for short packet lengths, and the control channel also has short packet lengths, but they are not the best ones. We can have better codes than these particular polar codes. You can achieve much better polar codes with different design. And so that's why we have to redesign error control codes for 6G. So we have used combined AI and analytical methods to design LDPC codes, short LDPC codes, and short polar codes with high reliability, low delay, and low complexity. So this is one example of a new end-to-end error control code design, where we designed an encoder by using a deep reinforcement learning method, and we used decoder with the combination of an analytical belief propagation decoding method in which we embedded graph neural networks. And so effectively, we also combined here analytical and AI methods, machine learning methods. And so without going too much into technical details, I will just show the result here, which shows the improvement of the new LDPC codes designed by this method compared to the standard LDPC code, which is about 1 dB in the signal-to-noise ratio and 1 order of magnitude in the bit error rate. And this could be further improved by jointly training the encoder and decoder. So this code is a possible better code for URLLC for 6G. We used a similar approach to design short polar codes, because as I said, these codes in the 5G are not very good. So we can use, again, a combination of analytical methods and AI to design a range of short codes of length 512 to 4096. That would be the limit of the length that would be used for URLLC. And we achieved high reliability and lower signal-to-noise ratio compared to the 5G polar code with CRC. And the gain is about 0.3 dB in the EB on anode, which is the bit energy per noise spectral density, and 1 order of magnitude improvement in the error rate. And these codes are also candidates for 6G networks. In all standards, we use now adaptive codes. So in this control channel, we use adaptive codes with only 4 different rates, because for the control channel, we don't have much variations in terms of applications. But for 6G, the system has to support a huge range of applications and various application environments and variations in the channel conditions. So we should have a much higher range of code rates. For example, if we have a code of length n, we should have 1,000 different code rates if we want to have bit level granularity, and that's what is required for 6G. So here we designed an adaptive scheme with polar codes with bit level granularity, which achieves better performance than 5G codes in terms of the EB on anode, but also in terms of the EB on anode, which is signal-to-noise ratio, and is from 0.1 to 0.5. But in terms of the error rate, it is about 1 order of magnitude, only on Gaussian channel. And it is expected that the increase will be much higher for non-stationary channels, which have much higher variations in the type of the distribution of the channel variations, and also in terms of the application environment, and also in terms of the decoder complexity. Massive MIMO, which means massive multiple input, multiple output systems, is the main technology for 5G, which achieves a high data rate improvement relative to 5G. So what is massive MIMO? As opposed to 4G, we have here a much larger number of antennas at the base station, and we have a distributed antenna formed by a large number of users, so that we effectively have a large number of antennas at the transmitter and at the receiver. So this is massive MIMO at both ends. And so we have here a large number of mobile phones receivers that transmit simultaneously at the same time and within the same bandwidth to the base station, and they form interference between each other. So by using ordinary receivers, they would just collide with each other. We wouldn't be able to get anything. However, by using advanced signal processing at the base station, it is possible to remove all interference and get clear signals. So the receivers that are used at present are minimum mean square receiver, which inverts the channel matrix, and that is the way that it removes interference. And the one that has the best performance complexity ratio at present is so-called expectation propagation receiver, which is based on a belief propagation of messages between these users and antenna elements in the base station by using some calculations of posteriori probabilities of transmitted signals. So in our approach, we used this current belief propagation method, and we embedded graph neural networks, deep neural networks, in the nodes, which are those users and antenna elements, and calculated these messages by using neural networks instead of analytical formulas. So this provided a much higher gain compared to the EP receiver of 4.5 decibels in terms of signal-to-noise ratio, and 3 orders of magnitude in terms of error rate compared to the EP algorithm, the best known algorithm, and more than 4 orders of magnitude from the commonly used method, MMSC. So this was done for the number of transmit antenna 64 and the number of receive antennas also 64. The number of users is 64 and the number of base station antennas is 64, 16 QAM modulation. The complexity of the receiver is of the same order as the complexity of the EP receiver, which grows as the cubed number of users compared to the conventional receiver MMSC, which grows with the squared number of users. And so these are numerical values for 256 number of users and antennas. And so the complexity is 28 times 10 to the 7, which means the number of operations that the receiver does. And so it is 1 order of magnitude higher than MMSC and about 64% higher than the EP receiver. So this is the final slide, which shows a way of implementing the wireless cellular networks, so called Open Radio Access Network, ORAN. So ORAN is a method that replaces traditional wireless networks by traditional wireless networks which are proprietarily vertically integrated. So ORAN replaces it by open and interoperable units of network implemented in software. So while traditional network is done by specialized software running on specialized hardware, ORAN is based on the standard software running on general purpose hardware. So by doing this, enterprises have opportunities to deploy their own customized networks, private networks, tailored for their own application requirements. And so that would foster innovation, speed up the time from general concepts to commercialization, and reduce costs of private networks, and increase the number of vendors that sell the network equipment. So it is expected that O-RAN will play a modest role in 5G, but will be fundamental in 6G. So this picture shows the deployment of O-RAN worldwide. In Australia, we have already an O-RAN deployed by Optus for services in remote areas. We have implemented an AI-designed 5G O-RAN in our lab. And we have some selected 6G modules on that. So it gives us a platform on which we can deploy and test our algorithms. So in summary, I showed the vision of 6G, its technologies and applications, showed that AI will be a useful tool for the design of 6G network, but in combination with AI. If there is the main message from my talk, it is that AI is not enough. It has to be used with analytical methods. And that 6G will empower enterprises by distributed AI and bringing AI to devices, to the edge, AI and cloud capabilities. And open radio access network will lower network costs, foster vendor diversity, and promote innovations. So now there will be a video showing O-RAN deployment in our lab and design of a 5G small base station. And after that, I will be happy to answer your questions.
The deployment of 5G large base stations is underway worldwide. Current 5G base stations are implemented with specialized hardware, and the cost of manufacturing is very expensive. The development of open-source cellular systems is supported by the Open Source Radio Access Network Alliance, with over 30 international telco members. At our center, we've achieved a major breakthrough by developing open-source 5G small cell base stations that run on general-purpose hardware. These 5G small cell indoor units play a crucial role in providing indoor coverage for locations like shopping malls, office buildings, residential complexes, hotels, airports, and train stations. In collaboration with Telstra, we've also developed a novel 5G programmable scheduler, which has been adopted by the 5G Open Air Interface Standard. Our innovative 5G O-RAN systems offer superior performance at lower costs compared to existing 5G systems. Rigorously tested for reliability, our system is now ready for commercial applications and deployment.
Thank you, Branka. With brain-to-brain communication, I wouldn't have to look at this screen to see the questions that are asked. But let me follow a couple of the questions that have come up online. First one here we have is. I'm sorry. Thank you. The first question is, what are the potential health effects of the deployment of 6G, especially in terms of exposure to the higher frequency electromagnetic radiation?
Okay, thank you for the question. It is probably something that everyone is interested in, and there's always a lot of excitement and skepticism where new generation of cellular networks is deployed. So we quite recently had that with 5G, even some theories that 5G causes COVID. We just need to go back to fundamentals and see what frequencies are involved. So in 5G, we use microwave, which is also used for 4G, that is below 6 gigahertz. And we use millimeter wave, which is from 20 to 50 gigahertz. In general, it could be up to 100, so we might continue using the whole millimeter wave spectrum. And in 6G, we will be using both microwave and millimeter wave, and we will expand it to the terahertz band, which is between the current radio waves, between the microwave, which is 100 gigahertz, to just below the infrared radiation, which will go from 100 gigahertz to 10 terahertz. So all three bands are non-ionizing radiations. The radio waves don't have enough energy to cause chemical changes within molecules. So they cannot actually break chemical bonds within molecules, as opposed to ultraviolet, which is from the sun, then higher X-ray and gamma radiation, which can produce chemical changes and can possibly, in high dose and over a long time, can cause cancer. While these three radio bands have been shown to cause only thermal effects, which means heating the tissue, but in wireless cellular standards, we have specification how high the power should be. So the power is specified to be below a certain level, not to cause temperature changes. So below the ultraviolet radiation, there is only thermal effect of radiation, and there is no danger of DNA changes and cancer.
Thank you. Thank you. There's microphones going around here if there are questions in the audience. Yep, Fiona.
Thank you very much, Branka. That was a fabulous talk, and I really appreciated hearing the history of your contribution to the intellectual property underlying our whole industry. Just for transparency, my name's Fiona Marnie. I work for Telstra. So I have two questions about the involvement of AI in 6G. First one's a bit technical. So you talked about how you're using these graph-based neural models to enable the operation of 6G on standard hardware. So my question is there a need for supporting compute capacity, so as in edge compute capacity to support that if the models are running on standard hardware? That's the first question. Second question, quite different one. We've seen an explosion of AI over the last 12 months, particularly with large language models and concerns around governance and ethics kind of within the community. So I suppose my question here is, do you feel that the maturity of our approach to AI is moving fast enough to be able to, for instance, to be able to have the transparency that we might want, and the concerns around ethics, say the intellectual property in the training of large language, of your machine learning models?
Yeah, okay, I'll see. Let's go one by one. So the first one, whether we will need computing power of AI at the edge. Is that right? Yeah, definitely we do, for many reasons. The first one is for latency, reducing latency, because we have seen the importance of latency for many applications. So instead of sending signals from sensors on robots, for example, or manufacturing plants, to the cloud, and waiting to receive the response, which might take a long time. So we can send it from the robot to the edge computer located close to it. So this is how we can reduce latency and enable stable control. So that is important for mission critical applications. Second is transmitting a lot of data over wireless network costs bandwidth, money, and can cause network congestion. So instead of sending it to the cloud, it's better to send it from the communication point of view, send it to a closer edge computer. The third very important one is privacy and security. So we don't need to connect for the privacy and security point of view the edge computer to the internet in order to prevent cyber attacks and to preserve privacy. So these are three main reasons, for example, for having that at the edge. And the second, I don't quite understand that, first, I'm not an AI expert, so I'm not developing AI as such. I'm only using AI, but we still have to know a lot about AI, to choose appropriate methods, and also to do training and to, even in some cases, design communications together with computing, as we mentioned, because we need to distribute AI to various points in the network where it is needed. So I'm probably not a person to respond to the AI design as such. So I'm using it, but I'm not developing AI methods. So yeah, there are many issues there, even for us. It's for example, for brain to brain, that will be also AI. There will be many, apart from technical, many ethical and privacy issues, and that is the same with AI. So these all need to be addressed prior to actually deploying widely AI. And we as a university, we deal now with how to use AI in teaching and assessment of our students. And in teaching, how we can constructively use AI capabilities, not to ban them, but to actually use their full potential in a creative way.
Any more questions? Mark?
Probably talk loudly enough. Branka, thank you for a wonderful lecture. I have to say much of it was way over my head, but the vision that you showed us for intercommunication was remarkable. Now, one of the things you touched on was underwater communication. It's a silly question, but does that render the manned AUKUS submarines irrelevant and outdated already? And does it herald the foretaste of underwater drones, unmanned drones, in this complex world in which we live?
Thank you for the question. I can only say that from communications point of view, we will allow these technical opportunities for many applications. And I have not been working on even drones or any applications. I've been only working on communications. So, and 6G will provide that opportunity for various applications, but then other people from other areas will use them in the same way. At the time using AI to develop communications, they will use communications to develop other services. So yeah, there are opportunities for many new services for underwater communications, yeah.
Thanks, Branka. Branka's very, very modest, and over 40 years, Branka has not been patented any of her IP or the team's IP. It's all been distributed so that the industry can move forward, and I think that is a terrific thing about Branka. Let me pass over to. Let me pass over to Dean Willie Zenopol to thank you.
Okay, thank you, Jeff.
Okay, Branka. I want to really thank you for a wonderful talk. I know it's always very hard to give a talk that is, appreciable by a general audience and to at the same time show some of the depth of your research. And I think you've definitely succeeded in doing that. You gave a very nice vision of what the future of communications is. It's a field that has grown tremendously. I remember doing my own PhD thesis over a 1200 volt modem, if some of you still remember what that is, to buying my first cell phone in the late 90s, where you had to go sit by the window to get enough coverage, to be able to carry on a conversation. To yesterday, when I was in a bus from Canberra back to Sydney, and I was on a Zoom call, and everything just worked perfectly. And I think you've sort of given a wonderful vision of what the future of the field and its future possibilities look like. I think you also gave sort of a glimpse, to the extent that you can do it for a general audience, of the depth of your work and sort of the future of the combination of AI and telecommunications. I think that's indeed where the future is. Now, beyond just thanking you for the talk, I also want to thank you for your many contributions to the school and the faculty and the university. I think you're the one that has put University of Sydney on the map as one of the prime institutions in telecommunications research. And more than that, my previous institution, EPFL, as you know, is also known for its work in communications. People like Rudiger Urbanke, that some of you may know. But it is theory. These are paper and pencil people. These are mathematicians, very good ones, but still mathematicians. You've also been able to apply some of the telecommunications work that you've done to real applications. Some of them were mentioned by Jeff in the beginning, power networks and robotics. So I think that's really brought an extra flourish to your work and to what we can say here about what happens at the University of Sydney. So we have a little token of appreciation for your talk and your work. But before I get into that, I want to thank a few other people. First of all, I want to thank the Warren Center for putting on this event every year. And I want to especially thank the working group that every year sets up this talk, headed by John Lear. It's a wonderful event for the faculty, and I want to thank all these people involved for putting that on. Also want to thank the staff of the faculty that assisted in the communications team that assisted in putting the event on, and the Niels team, who, as always, made it all go off without a hitch. Thank you all. Finally, I want to thank everybody, both online and here in the audience, for coming to the talk. Now, like I said, we have a small token of our appreciation. It's basically a gift certificate that we will give in your name to an organization called, a funny name called Deadly Science. It is an organization that promotes science for Aboriginal kids, so they get involved in science and engineering. So with that, I would like to thank everybody again. I would like to especially thank you. I will give you the little certificate, and then I will call the innovation lecture to a close. Thank you all. Okay.